for eigenstates is pretty trivial. It's almost, you can always do it by inspection, but if you want to be thorough, I won't even do it because it's pretty obvious. All right. Okay. Now, physically, what's going on? These four eigenstates, these four eigenfunctions. What are they? Well, three of them. These are the following three. So up 1, up 2, and then 1 over root 2, up 1, down 2, plus down 1, up 2. So here, and the third one, down 1, down 2. Those three eigenfunctions, they are three of a so-called triplet states. This triplet, there's three of them. Okay, and they're meant to be when the two spins that you have, S1, S2, when they're both oriented, let's say both up, well, they're both parallel. They might be both up or both down. Or I'm a bit fuzzy about what this is supposed to mean physically, but oh, maybe both like that. I'm not sure. Anyway, so these three are. That's probably it. So both of them are both up for this case, and this one are maybe like that, or like that. Question mark about this one, and this one probably both down. So in other words, the total angular momentum is 1, right? Yeah. So I suppose this one is they're both like that. So so for these three eigenstates, the orientation, if you like, of the two spins is they're parallel. They're both pointing. The two of them are pointing in the same direction. So the total angular momentum is 1. So a half plus a half, effectively. Right? Now, if the total angle L, that's an allowed L. It's a total now. L is L1 plus L2, if you like. So for the total system, the number of components along the z-axis will be 2L plus 1. Right? We've done that before. It's just revision. Now if L is 1, so you get 2 times 1 plus 1. That's 3. So you'll have 3 m values. Remember, m is the eigenvalue for the z component. And remember, m ranges over minus L to plus L in jumps in steps of 1. So L's 3, 2L plus 1 is 3, L's 1. So the three possible values of m will be plus 1, 0, and minus 1. Right? Now the fourth one, it's called the, because there's only one, the singlet state. Right? Remember, you've got a minus here. Now it's interpreted to be when the two spins are anti-parallel. So you might have like that, or like that, I guess. Well, I think it's just that. It's just like this, right? Anti-parallel. And the total angular momentum is L is 0. Okay. So your total angular momentum. So S1 plus S2 would be 0. Now, you can talk for these four states. Remember, I've done this kind of thing before, but to calculate an expectation value, meaning the average measured value, you need two things. You need the operator and you need the wave function that you're talking about. Now, in this case, the wave function is this. So if you want to find the expectation value of S of Z, now S is the sum of your two spins, S1 plus S2. So you just plug this into here on the right in the ket, and here on the left with the bra. And you can do that for homework if you want. And you'll get plus H bar. I can almost do that by inspection. Look, SZ is S1Z plus S2Z. Now S1z acts on this one. That will give you an eigenvalue of h bar over 2. Right? And the S2z of this acts on this one, and that will also give you an eigenvalue h bar over 2. So you're adding those two, so you'll get an 2 times h bar over 2, so it's just h bar. Right? So you can take the h bar outside, and then you're just left with a bracket of this with the equivalent bra. And these are also normal, so you just get 1, so you're just left with h plus h. Now, what about this one? It's a little less obvious. Doing it verbally real time here. Okay, so Sz again is S1z, I'll say z, S1z plus S2z, right? Now S1z acts on this, so you get plus h bar over 2, and here the S1 acting on this will give you a minus h bar over 2. So you've got there are 4 terms, right? Here you have 1, 2 terms, and this is 2 terms, S1z plus S2z. So you get 4 terms. Now, when you got you'll have a minus h bar here for this, and when the z2 operates on this one, you get another minus. I guess the two there'll be 2 minuses, 2 pluses, and I guess they cancel, and hence you get 0. Yep. Now this one will be similar to this one, except instead of having plus h bar over 2 as your eigenvalue, you'll have minus. So you'll have 2 minuses. So you'll end up with minus h bar. Okay? So you can calculate the expectation values for SZ for these 3 eigenstates, the so-called triplet states, because there's 3 of them, right? Where the total S is 1. Alright, now for the singlet state, that's when you have a minus here you've got a plus. When you have a minus here, total S, just S, is 1. Sorry. And the expectation value will be 0. Why is that? I guess it's similar logic to here. Right? You'll probably get 2 pluses and 2 minuses, and they cancel. Right? So the expectation value is 0. So when you have these sort of mixed terms, this superposition, the expectation value is 0. 0. Right? Okay. Now a more general comment, just finishing off this session. In general, in quantum mechanics, when you have 2 systems, and they both have angular momentum, there is a way within quantum mechanics you can add those 2 angular momenta. So angular momentum L1 and angular momentum L2, and as operators, you'd make them both operators, hat L1 hat and L2 hat. You can add them, and you will get a general, like a total angular momentum, just L hat. And doing this is, we'll do it a bit in this text in chapter 9, so you have to wait 2 more chapters. We'll do it to some extent, but doing it full-blown with group theory and representation theory from pure math and all that stuff, that's well into graduate level. So I know if you've done the pure math for representation theory, then you could probably do the full quantum mechanics angular momentum addition at M2, I'd say, M2 level, second year masters. Right, well, that's the end of that session.